Hello everyone, welcome back. In the last class we saw about the wave nature of the hyperbolic equations, and we basically noticed that there will be two characteristics if it is a 1D wave equation, okay, and they will be traveling with x plus ct and x minus ct, okay, and all the solutions are basically depending on what is your domain of dependence and what is the region of influence, right. So, let us say if you have a wave which is governed by this equation, okay, del to u by del t square equal to c square del to u by del x square, right. So, if the wave is marching in time, it will have two characteristics x plus ct, okay, and x minus ct, right, and then we will have basically the any solution at any given time. So, let us say if I am here at x 0 t 0, okay. So, this is your domain of dependence and this is your region of influence, right. So, the solution will be bounded like this, right, and we also saw that your solution u would depend on basically this x plus ct, f x plus ct plus g x minus ct, right. So, if it is like equation which is like given by del u by del t is equal to c du by dx, okay, and then this is you have just one characteristic, okay, and your solution at any time x t will be basically u 0 x minus c t, right. That is what we saw in the last class, right. So, instead of depending separately on x and t, okay, you have the initial waveform which is u naught, okay, and whatever initial waveform that you have, okay, you just keep on shifting depending on the wave speed, right or left, okay. So, if it c is positive, then it will shift on the right, if c is negative, then it will shift on the left, right. And in this case, these are called the right running wave, okay, and this is the left running wave, okay. So, this is when c is constant. So, basically it is a linear convection equation. What if the c is not a constant, but let us say you replace c by u, okay. So, now your equation is del u by del t equal to u del u by del x, right. So, it is a non-linear convection equation, and more accurately it is a quasi linear, right. And so, now the convection of u depends on u itself, right. So, it will depend on your initial waveform, right. So, to show that what we did in the last class is basically let us say this is your initial waveform, okay, it is a Gaussian waveform, okay, and if you use the linear convection, okay, then what will happen, it will just convect on the right like you see in the blue one, and whatever difference that you see from here to here, that should not have happened if it were an completely accurate solution, because there is no dissipation here, okay. If you have a dissipation, then equation will look something like this, del u by del t plus u del u by del x equal to nu del to u by del x square, okay. Now, you see we are bringing in the elliptic nature, okay, through the viscous term. So, nu is the viscosity, you can think of as the viscosity as positive quantity here, right. So, these kind of equations are called the convection diffusion equation, and more appropriately here it is a non-linear convection, okay, which is the left part, and diffusion, okay, which is the right part equations, okay. It is also named after a mathematician, his name is Burgers. So, it is also called the Burgers equation, okay. So, if you have equation like this, then you would see that it will not only convect, but it will also diffuse based on the viscosity that you have here. But here it is I have not used any diffusivity here, any viscosity here, still it is diffusing. This is due to the numerical diffusivity, which will come to discuss when we talk about the discretization and different numerical approaches, right. But ideally, if you have an expression like this, it purely means that the wave u moves with time, and basically if c is constant, then it will move with a wave speed of c. If it is not a constant, then it has to move with the wave speed of u, right. So, this is for del u by del t plus c del u by del x equal to 0, but this is not actually 0, there is some numerical diffusivity, and that is why you have there is some attenuation here, okay. And this one is for the del u by del t plus u del u by del x equal to 0, right. So, what do we observe here? That because see the wave speed is the waveform is as such that the u is higher here and lower here. So, the lower part is moving slowly, okay, and the top part is moving fast, right. So, because of that at certain point if you keep on moving it like that, okay. So, because this is moving fast, this is moving slow, okay, you will have a shape which is like this and this looks like a sock, right. So, to explain it more clearly I have taken some more examples, okay. So, I will talk about two different shapes. So, this is one shape, okay, which is given by this expression, okay. So, if x is less than 0 then it is 0, if x is greater than 0 then it is x, right. So, you have a wave which is like this, okay. This is the profile that the black one that you see here, okay. Now, we are using the same equation del u by del t plus u del u by del x equal to 0, right. So, what will happen? So, the velocity here is higher, here it is lower, correct. So, this will keep on basically the difference will keep on increasing, right. So, this is a case of what you have read earlier is the expansion fan or the rarefaction wave, right. The velocity is 0 here. So, it is fixed here, okay, but depending on how I mean how the u is changing, this is also going on the right hand side. So, this is what if you recall what we read in the theoretical part. So, if you have a basically flow which is coming from this side and this is let us supersonic flow, and what will happen at this point because it has more places to expand. So, you will have this expansion wave, the same nature you are seeing here, and that is coming because of the nonlinear nature here, right. Now, if I do if I change the initial waveform, so this is what is shown here, okay. This is at t equal to 0, then 0.2, 0.4 and 0.6, okay, solving this equation, right. Now, what we do will change the waveform, okay, and now my waveform is there is a negative slope. So, x less than 1 is 1 minus x and x greater than 1 is 0, right. So, we have a slope which is coming like this, right. Again the same thing, the velocity is higher here and lower here, right. In fact, it is 0 here and this is low and then it keeps on increasing like this, correct. So, what will happen is that as the time progresses, it will move faster and faster like this and like this and like this, and it cannot go beyond this line because it otherwise it will become a multi-valued function, okay. So, that is why eventually what will happen, you will have a shock which will develop here, okay, and that is purely coming because of the non-linearity as we have been discussing, right. So, now we have seen two situations, okay. In one case you are seeing the formation of a shock, and there is another case we had a situation where we saw the expansion waves. As you have read earlier that the expansion wave is an isentropic phenomena, okay, but shock is not isentropic, it is a very strong discontinuity, okay, at a given line here for example. Okay. So, if you want to solve, let us say I mean there is a conundrum here, that means that we are trying to solve del u by del t plus u del u by del x, okay, and we are getting a solution which is a strong discontinuity, okay. So, things are changing very drastically here. So, a very high velocity becomes very low, right. So, that means your differential is not defined here, del u by del x is not defined, right. So, how are we able to solve it, right. So, there are couple of things that we will discuss later. One is called the integral formulation. If we solve it in an integral form, you do not have to have the exact, you do not need the exact derivative here like del u by del x, okay. The other is a weak formulation, okay. We will multiply this with another function which is more smooth and we will transfer this derivative to that smooth function, okay. That is the weak formulation. And third is basically you can add some dissipation, so that rather than this thing happening in very small narrow region, it can happen, it can smear out and it can basically form shocks like this or slightly thicker, okay. So, basically if you are doing finite volume, you are using the integral formulation. If you are using finite element, then what you are using is the weak formulation, and if you are using finite difference, then what you are doing is basically you are adding some dissipation to smear out the shock, right. If you do not have that, for example, if you central differencing, your solution will blow out, okay, because there is no dissipation there. So, we will look into all these details later because the course is about the computation of this kind of flow phenomena, right. So, I hope you appreciate the hyperbolic nature of the PD and what happens when the nonlinearity kicks in. Right now, the question we have is, can we show that the Euler equation that we have that we saw earlier is hyperbolic, or what kind of classification we can give to this kind of equation, right. So, this is written in a conservative form, and you can see we have this rho u and rho e, and Fu is given as rho u square plus p and rho e plus pu, right. So, somehow we can write in this form, okay, and we can show that Au has got basically the eigenvalues, okay, which are real, okay, and then you have eigenvectors also, okay. So, as we have discussed earlier, then we can show that basically this is a hyperbolic form, right. So, this is using the conservative form, this is slightly more tricky. So, we will go with the primitive form, and then I will also show the steps of the conservative form, okay, that you can go back and work at home, that how do we get the eigenvalues of Au. First of all, how to get this Au, because Au, as you can see here. So, if you take this expression, this is du by dt plus, basically you can write this as del f by del u and del u by del x equal to 0, and this is nothing but Au. This is called the Jacobian, right. So, this is del u by del t plus Au del u by del x. So, first thing is to find out what is the Au, and then get the eigenvalues and so that they are real, okay. If they are real, then you will have it is a hyperbolic system, right. So, instead of working on conservative, I will first show you the non-conservative form. So, non-conservative form I am choosing, basically this V is now the non-conservative primitive variable. I am choosing rho, u and p, 3 primitive variables. Okay, so, we have seen the expression for basically rho. Okay, this is the same expression that we had here earlier, del u by del t plus del rho u by del x, right. So, you can basically expand it, rho del u by del x and plus u del rho by del x. Why we are doing this? Because we want to cast in the form of basically del by del t of rho u p and plus we still want del by del x and some form of basically rho u and p, okay, basically combination of rho u and p, okay. So, we have written here, and here you will have basically rho u and p, because we are writing in dv by dx, okay, and then there will be ap of v, okay, this the Jacobian of the primitive variable, right. A underscore p represents for the primitive variable, solving in primitive. So, for rho we already have, for u also you can do the same thing, bring the pressure term on the left hand side. So, we have basically rho u and p here also, okay, and then energy we have, I am using the internal energy equation, because I have to get the pressure form for this. I want an expression which has got del p by del t plus whatever you have, okay, equal to 0. So, I have taken this internal energy equation, okay. This is the pressure work and this is the total change in internal energy, we have derived it earlier, and so now the pressure can be written as P equal to gamma minus 1 rho e, that's this we have seen earlier, okay. So, they basically E equal to CVT, right. So, CV basically RT by gamma minus 1, right. So, multiply it by rho, so rho E is equal to rho RT by gamma minus 1, which use the ideal gas equation, this will be P by gamma minus 1. So, P is equal to gamma minus 1 rho E. Why we are doing this? Because we already know the expression in terms of E, we want to get the expression in terms of P. Okay. So, now you take the total derivative on both sides. So, you will have d by dt and d rho by dt. Okay. So, d rho by dt again you can use the expression that we had discussed earlier, the continuity equation, this is the continuity. Okay. If you recall, we have said that if it is incompressible, then this term goes to 0, and that is why you have this del dot equal to 0, right. So, that is a continuity equation written in the form of total derivative. Okay. So, you put the d by dt from here, rho d by dt and d rho by dt from here, okay, and you will get this expression from this, okay. And then what you will do, you basically combine this del dot u and you have this minus, so what are the things that you have, this is E rho, okay, and E rho we know that p by gamma minus 1. So, you can take this thing you take this common del dot u into p, yeah, you can take that out, and that will become minus gamma minus 1 and minus this was E rho. Okay. So, this is minus gamma minus 1, I am taking p dot u, and this is basically p by gamma minus 1, right. Rho is p by gamma minus 1, right. Yeah. So, you can take this together and then work that out. So, this is p by gamma minus 1. I think there is probably some mistake here. Okay, you can just let me check. Okay, so this is gamma minus 1 and then rho d by dt. So, let me just work it out from here, probably it will be done, or maybe you can just go back and check it. Okay, ultimately what will have that you will have the minus plus minus p will get cancelled out. Okay, and ultimately you have this expression which is the gamma p into del dot u, right, and you can write it for 1d. So, this dp by dt can be written as del p by del t plus u del p by del x. Okay, this is the total derivative we written like that, and for 1d this will become equal to minus gamma p del dot u del u by del x. Okay, and you combine all of this together, you will have this expression, right. Okay, so then we have all these expressions that we wanted to see, the rho u n p, okay, and put it in this form. Okay, so if you put it in this form, so pick the del by del t term. Okay, so this is rho u p. I am making a vector equation now in the matrix form. Okay, and then I have an expression here which multiply to basically del by del x of rho u n p, right. That is what you want, right. So, if you look at the first expression here, so del rho by del t, that is done from here. Now, this is u del rho by del x. Okay. So, this is u into del rho by del x, okay, and plus rho del u by del x. So, rho del u by del x, there is nothing containing p. So, that will become 0. Similarly, look at this term, the first term is through this time derivative, and then you have u del u by del x. So, there is nothing with respect to rho. So, this goes to 0, and this is u del u by del x, and then this is 1 by rho, right. And then similarly, you can have the p. So, this term will go here, and this is u del p by del x. So, the u will come here, and del u by del x is gamma p, and this will be 0, right. Now, you have this matrix, and what we want to do, we want to find the eigenvalues and eigenvectors of this AP. So, if you want to get the eigenvalues of this AP, you will have this AP minus lambda I equal to 0, right, that is what we want. So, this will become u minus lambda rho 0 0 u minus lambda 1 by rho and 0 gamma p u minus lambda. Okay, the determinant of this should go to 0, right. So, you take this, okay, because these two are 0. So, this will become u minus lambda, okay, and then you have this u minus lambda square minus this is gamma p by rho equal to 0, right. So, that will become u minus lambda square minus a square is equal to 0, right. So, what are the eigenvalues that you have? First is u minus lambda equal to 0, that means this lambda 1 is equal to u. Another is u minus lambda square minus a square equal to 0. So, this is u minus lambda is equal to plus minus a, right. So, that means u 2 is equal to lambda 2 is equal to u plus a, and lambda 3 is equal to u minus a, right. So, we have got 3 eigenvalues, and all 3 eigenvalues are basically real. Okay, this is the flow velocity and this is the speed of sound, right. So, all the 3 waves that we have, there are 3 characteristics that we found for this expression by casting it or writing it in the primitive form, and all 3, this u plus a and u minus a, they are all real, they are all real characteristic. That means, it is a hyperbolic system, right. And then what you can do, you can basically get this eigenvalues also. So, you have AP is already there, multiply with this L. Okay. So, this is the definition of eigenvector, we are trying to get this left eigenvector. So, L AP equal to lambda L, and please go back and work this out. This is the basic linear algebra that have been studied, and you will get this eigenvector, left eigenvector, which will look like this, right. So, then what we did here, that we proved that it is an hyperbolic system, the Euler equations. Now, we did for 1D, okay. For 2D also, so when you have 2D, you will have del by del x and del by del y term. Okay. So, you have to basically look at the locally 1D region if you are trying to solve in a domain, right. So, for example, if you want to solve in a domain like this is 2D, right. So, locally if you look at this is the 1D domain. So, you have might have velocity u here and v here, right, but you have to look at the velocity which is normal to this, okay, and that local direction, okay, local you can have this locally 1D Euler equation, and that is where you will see the hyperbolic nature of the PDE, okay, and similarly you can do for 3D also. So, now we have this left eigenvector also. So, what we can do, we can multiply this left eigenvector with this expression that we have. So, multiply this entire thing by L, okay, and what you do basically you take this now LAP is equal to lambda L, right. So, you can write it L del V by del T plus LAP basically lambda L, okay, del V by del x equal to 0. Now, you basically do this LV equal to, let us say, call it equal to W, right. So, now it will become del W by del T plus lambda del W by del x equal to 0, right. So, once you write in this form, why did we write in this form? Is because if you look at the lambda here, so lambda has as we saw lambda 1, lambda 2 and lambda 3. I have basically written it in u minus a, u plus u and u plus a. Okay. The reason for that is there is something which is basically equal to the flow velocity. The another one is flow velocity minus the speed of sound, and another is flow velocity plus speed of sound. Okay. So, I have written the in the increasing order of the wave speed here. Okay. Now, if you look at this lambda, okay, so they are basically it's a matrix which has all the off diagonal terms are 0, right. That means this system is decoupled, right, because only when you are looking at the, let us say, the top equation, okay, so only this one will work, okay, and the middle one only this one, and the bottom one is this one, right. So, what we did, we decoupled this equation. Okay. Earlier we had an expression where the AP, if you look at in the last slide, okay, this was the form of AP. So, this was the coupled one, all three equations were coupled, but if you write in this form which is del W by del T is equal to lambda del U by del W by del x. So, basically you have this completely decoupled equation, and when it becomes decoupled, then we say this independent wave amplitudes, so if you have W as W1, W2 and W3, okay, they are all propagating at speeds u minus a, u and u plus a. So, W1 propagating at u minus a, W2 u, and third is u plus a. So, whatever initial u waveform you have, if you express in terms of W1, W2 and W3, you can see the they are propagating at characteristic speed of u minus a, u and u plus a, okay, separately. So, you can write this in the decoupled form like this, okay. You can see this I can go equal to 1 to 3, okay, and if you multiply this, so if you go back and multiply this L into V, right. So, you will get the W, and the W will be the W1 will become like this, and W2 is rho minus P by A square, and the W3 is basically rho by 2 A U plus half 1 by 2 A square P, right. So, these two are basically called the acoustic waves, and this is in fact you can go and show that this is equivalent to the equation which is ds by dt equal to 0. We will come back to this, whereas is the entropy. Okay. So, this is called the entropic wave. Okay. So, the entropic wave basically moves at the speed which is u, and then we have something which is moving at u minus a speed and something is moving at u plus a speed. Okay. So, this is called the left running acoustic wave, and this is the right running acoustic wave. So, if you write in this form, basically you have three different waveforms W1, W2 and W2, W3, they are moving at different speeds u minus a, u and u plus a, right. So, we are basically looking at the wave nature of the Euler equation, okay, and this will be very useful when you are basically trying to get a numerical solution of this equation, and also when you try to do the boundary condition, right. So, for example, if you have a supersonic flow which is basically traveling the positive x direction. So, you can have basically three things. This one is del x by del t equal to u minus a, another is del x by del t equal to u plus a. So, the entire solution like we discussed earlier. So, this is your domain of dependence and this is the region of influence, and let us say you are at this point. So, you will be only affected by this and it can only affect the solution which is on in this region that we have, right. So, it is similar to the picture that we drew earlier for a wave equation, right, but this is the wave, the nature of the waves are very different. Now, we have the entropic wave and then we have the acoustic waves also which are traveling at u minus a and u plus a, okay. And these can develop the shock waves, even the contact discontinuities, okay. Now, I will just briefly show how you can get the same thing using the characteristic form. So, we had skipped it earlier saying that it is complicated, but I am just showing you for your reference. You can probably go back and do the math, right. So, our purpose is basically del u by del t plus a del u by del x equal to 0, right. So, the here a is equal to dA by du. So, how do you get this du by du, right. So, let me just show you. I have written the final expression here, but how do you get it? So, you can write this u as u1, u2 and u3, okay, where u1 equal to rho, u2 equal to rho u and u3 equal to rho e. And you also express f in terms of u2, u1 and u3, okay, and the conserved variables. So, because the first one if you recall del f by del u by del t, sorry, del rho by del t plus del rho u by del x equal to 0. Now, rho is equal to u1, right. So, this is basically del u1 by del t plus del by del x and rho u is equal to u2. This is the first one, right. So, this is how it will be written. This is u and this is u1, this is u2. Similarly, you have to write the second one also which is rho u in the conservative form and what is the expression in the flux fu, write in terms of u2 and u1 and p I have written separately, but you can also write p in terms of u1, u2 and u3. So, everything you have to write in these variables, okay. And similarly, you can write for the energy which is rho e which is u3 and you can write it in this form. Now, if you look at you want what you want to get a Jacobian which is basically del f1 by del u1, del f1 by del u2 and del f1 by del u3. That is the top one, okay. And then you have del f1 by del u, sorry, del f2 by del u1, del f2 by del u2 and del f2 by del u3, and similarly del f3 by del u1, del f3 by del u2 and del f3 by del u3, right. So, we need to get this derivative. So, now everything is written in terms of u1, u2 and u3. So, if you take, let us say this is my f1, right. So, if you want to do f1 by u1, so del u2 by del u1, okay, that will be nothing but 0. Now, you go to the second one which is basically del f1 by del u2. So, this is u2 and this is u2. So, this is del u2 by del u2, that will become 1, and then you have del u3 by sorry, del u2 by del u3, that will also become 0, right. So, we got the first row. Similarly, you do for the second row. So, this is the second flux, this one, okay, and you take that and p is also given, you find this del p by del u1, del p by del u2, del p by del u3, put it all together, you will get this for del f2 by del u1, del f2 by del u2 and del f2 by del u3, okay. And similarly, you can go the last one which is the f3, okay, and you can do the same thing here. You get this basically divide it with respect to, take the derivative with respect to u1, u2 and u3 and you will get this expression, okay. Now, put it all together and you have to convert it back to the variables that we know, okay. So, this is the top row, this is the second row and this is the bottom one. Now, you put it back that u1 equal to rho, u2 equal to rho u and u3 is equal to rho e, okay. Put it back, you will get an expression like this, okay. Now, you take the again it is slightly complicated, you take the eigenvalue of this, okay. So, you will have minus lambda here, minus lambda here, minus lambda here and take the determinant of this, okay. And then finally, you will get again these three eigenvalues, okay, lambda equal 1 equal to u minus a, lambda 2 equal to u2 and lambda 3 equal to u plus a, okay. and this is what will it again shows using the conserved variables that this is an hyperbolic PD, which is expected, right. It is just that we took the primitive variable expression because it was easy to get this these three eigenvalues, but you can, if you want, you can do it using the conserved variable because both are the same equation. Okay, it's just we have cast it in a different way. When you try to do the numerics, okay, then it matters because as we saw earlier that the conserved variable conserve the property of this hyperbolic basically the telescopic collapse of all the terms within the interior region and only the boundary terms survive. Primitive variable do not show that. Okay, so that is also another important thing that will be necessary when you try to capture the shock. Right. So, we have shown that okay, the Euler equations, 1D Euler equations are indeed hyperbolic PDEs with three different characteristics u minus a, u and u plus a. Okay, so what I am going to do in the next class is basically I am trying to show that what is the integral form, okay, and what which is used in the finite volume formulation, what is the weak formulation, and finally we will also discuss about how do we do in the finite difference, how do we resolve the shock in the finite difference, because across the shock this del u by del x is not defined, right, but then you are able to resolve it through numerical schemes. So, what is special thing we do, what are the shock capturing schemes, right. So, those things we will be discussing in the next week. Okay. With that, thank you very much.